bust out some more AP review. This is 2012 BC free response number 4. All right, so we're given a table of values for f prime of x, and here's what we've got. The function f is twice differentiable for x values greater than 0, with f of 1 equaling 15 and f double prime of 1 equaling 20. Values of f prime, the derivative of f, are given for selected values in the table. Write an equation for the line tangent to the graph at x equals 1, and then use that to approximate f of 1.4. Okay, so I'm supposed to write an equation of a tangent line, right? So anytime we hear equation of a line, we need a point and we need a slope. So my point at x equals 1 is totally going to be this f of 1 equals 15, right? That is 1 comma 15. That's x comma y, right? And my slope is totally going to be f prime of 1, which is given to me on the table. F prime of 1 is an 8, right? So my tangent slope is an 8. So what that means is that the answer to the first part of this question is y minus the y value, which would be 15, equals m, x minus the x value, right? So the quantity x minus 1. So I get y minus 15 equals 8 times the quantity x minus 1. And that's great. They did not say that I have to write the tangent line solve for y, but if you want to solve it for y, the lazy way to do that is to add the 15 over and leave the 8 times the quantity x minus 1. So either of those are fine. Great. I wouldn't simplify it. I'm then asked to, so that's the first answer, right? Either of those is fine. If you want slope-intercept, you can. It's not a great idea. I'm then asked to use it, right? So I'm going to use y to approximate 1.4, right? So y of 1.4 would be a 15 plus an 8 times a 0.4, and that's a good reason not to distribute that 8. It's a lot easier to do 1.4 minus 1 and just get a 0.4. So that's a 15 plus 8 times 4 would be a 32, so this is a 3.2, so I get a value that is 18.2, which means that my f of 1.4 is approximately 18.2, and that's what they want, right? Cool. So, and they said, let's see, so let's make sure we did everything. We write the equation of a tangent line, correct. Then we use the tangent line, correct. So we did both things that we were asked to do. Let's do part B. All right, we're given a table, so there's a solid chance that we're going to be asked to do one of the area approximations or some kind of an approximation using this. So use a midpoint Riemann sum, so MRAM, with two subintervals of equal length and values from the table to approximate the integral from 1 to 1.4 of f prime of x dx. Use the approximation to estimate the value of f of 1.4. Show the computations that lead to your answer. All right, so MRAM, right? Anytime you're asked to use an area approximation method or an integration approximation method, you're told exactly what method it is, and in this case, it's MRAM. So we're supposed to use two equal windows, which means that we have to be using 1 to 1.2 and 1.2 to 1.4, right? Which means that these are my midpoint y values, right? Because the middle of 1 to 1.2 is actually 1.1. They gave you a table where that works. So the integral from 1 to 1.4 of f prime of x dx using an MRAM sum is going to be the width of this box, right? So the width is a 0.2 because it goes from 1 to 0.2 times the height of this box, and because it's MRAM, I'm going to use the midpoint y value, which would be a 10, plus the width of the second box, which is from 1.2 to 1.4, which is again a 0.2, times the midpoint height, which is a 13, right? So it's up to you. It is a non-calculator problem, so it's up to you how you want to deal with this. Timesing by 0.2 is not particularly awful, right? Timesing by 0.1 just move the decimal place one place. This just means you're doubling it. So this is going to be essentially you move the decimal one place, right? So this will be a 1, and then you double it, which makes it a 2. If you move the decimal one place, this would be a 1.3, and then you double it, so it's a 2.6. So you get that this is approximately a 4.6, right? Cool. Now, the next thing we were asked to do was approximate the value of f of 1.4. Well, we know that this integral, using the first fundamental theorem of calculus, should be f of 1.4 minus f of 1. This is a quantity that was given, right? And we were just told that it is approximately 4.6, right, based on our own work. So f of 1.4 should be approximately 4.6 plus whatever f of 1 was. We were given f of 1, so that means it should be approximately a 4.6 plus a 15, which would be a 19.6. All right, cool. Part C is where we finally see some BC calculus. So part C asks us to use Euler's method So we're going to use Euler's method, starting at x equals 1 with 2 steps of equal size to approximate f of 1.4. Show the computations that lead to your answer. So remember, Euler's method is actually essentially point slope, right? So the way Euler's method works is that we have some x and we have some y, right? And we can find the slope by using either dy dx, or in this case, f prime of x at a particular point, right? And then the way we find the new y, right, is we do the slope times the change in x plus the old y, right? Which is actually, if you think about it, if you did y minus the y value equals m x minus the x value, well, x minus the x value is change in x, and if this is your old y, you'd get y equals m times the change in x plus the old y, right? That's totally where we get that from. So if you ever have trouble remembering Euler's as like a fancy complicated formula, it's really just point slope sort of repurposed, which is true of an awful lot of stuff in math. So we're starting at x is 1, and we know the y value at 1 is 15. So my slope at 1 should be f prime of 1, which was totally given to me as 8. So my new y value should be my slope, 8, times my change in x. Now you'll notice that each one of these is going by 0.1, right? I'm sorry, no, it's going by 0.2 because they told me to go to 0.4 in 2 equal subintervals. So they want me to use 1.2 and 1.4. So my change in x is 0.2 plus the old y, which was 15, right? So I end up getting that this is a 1.6 plus a 15, which is a 16.6. So we put a 16.6 here. Then we did the same thing again. I want m, which is f prime of 1.2. Oh, look, thanks table, that's a 12. So that means that my new y, which is going to be my final answer, right, because this is the final answer that I want, is y at 1.4, is going to be the slope, which is the 12, times the 0.2, plus the old y, which is a 16.6. This is one of those moments to not be too proud to actually carefully do your math. And 2 times a 12 would be a 24, so this is a 2.4. Don't be too proud to write 2.4 plus 16.6, because boy, are you going to be mad if the reason you got the question wrong on the AP is that you were too proud to add carefully. So you end up getting a 19.0, so f of 1.4 using Euler's method with those 2 steps is approximately a 19. I'd put the 19.0 because we did the work to find the 0.0, so that's correct. All right, last bit, part D. Oh good, there's more calculus. Right, the second degree Taylor polynomial for f about x equals 1. Use the Taylor polynomial to approximate f of 1.4. Man, they're really into approximating f of 1.4 this time. This does tell us why we needed f double prime of 1, though. Right, so remember the way Taylor polynomials work, right? So I'm going to use p sub 2 to write this Taylor polynomial. So the first term, right, should just be f of 1, right, and then there's nothing else, right, and then we should have f prime of 1 over 1 factorial, right, times an x minus 1 to the first, plus f double prime of 1 over a 2 factorial times an x minus 1 to the second, right? And since it's p sub 2, I don't have to go any farther. I only want to go up to the squared term, right? Well, I know all of these numbers thanks to the table and everything else. I know f of 1 is a 15. I know f prime of 1 is an 8 over 1, so I don't bother to write it, times the quantity x minus 1. And I know f double prime of 1 is a 20 over this 2. If you want to make it a 10, great. 2 factorial is a 2 for the record. So I called it p sub 2 of x. I think they called it t or some other letter. It doesn't matter. Just don't use a letter that's already been used. I would not simplify. Honestly, this is fine. This is just fine. But if you want, you can go ahead and make it a 10 because that's what the 20 over 2 would be. Don't distribute things. You want to leave it like this. And then you were asked to use it to approximate f of 1.4. So the other reason you don't want to distribute is it's a heck of a lot easier to plug the 1.4 in and subtract 1. So this is going to be an 8 times the 1.4 minus 1, which is just going to be an 8 times a 0.4, plus a 10, oh, that was nice that they made it a 10 at least, times a 1.4 minus a 1 quantity squared. So I get that this is approximately a 15, plus we've seen this before, this 8 times this 0.4 is a 3.2, right? And then this is a 10 times a 0.4 quantity squared. Now there's a few ways to deal with this, because I get that that might feel like a little bit of a low blow, because this is a question 4 and therefore not a calculator. If I were you, I would do 10 times 4 tenths times a 4 tenths. I think that's the easiest way to deal with this. One of the 10s cancels with a tenth, and you end up getting 16 tenths, which is no big deal. It's a 1.6, right? Easy peasy, not a big deal. So you end up getting a 15 plus a 4.8, which is totally a 19.8. So you end up getting an approximate value of 19.8. So the cool thing about this free response, I think, is that they used 3 separate methods for you to approximate, 4 methods actually, for you to approximate f of 1.4. they used a pretty basic method where you find a tangent line to approximate. They used area approximation. They used Euler's method, and then they used a Taylor polynomial. So it's pretty cool that they used 4 different ways to approximate the same value.